So we can start right now. Okay, so hello everyone, welcome to our this month's IEEE CASS webinar talk. And today we're very glad to have the Dr. Janvi Giri from the NetApp to give us this talk. And before our honored speaker to do the presentation, I will first introduce some of our education activities from the CASS. And this webinar series actually is part of the CASS global education effort, and our goal is that to become a major resource for the education material provider for our CASS members and also the broad community members who are interested in the CASS of the field research and education activities. And actually, in addition to these webinar talks, we also have several very interesting and excited education activities, including the distinguished lecture program, the industry DLP program, and the many experimental learning in the hardware design, and also the job marketplace and the graduate opportunity posting, and so on. So if you are interested in those education activities, so feel free to get our information and join the CASS. So now let's welcome our speaker to give us a talk. And first, I will give them a very brief introduction to our speaker. Dr. Javi Giri is currently a principal architect at the technical industry lead at the NetApp and driving the convergence of the AI data infrastructure and the semiconductor workflows. And she brings over a decade of the experience across the semiconductor manufacturing, computational lithography, and applied AI/ML. Her work focuses on enabling scalable, product-grade intelligence across design and fabrication, including the agentic AI and autonomous manufacturing systems. And she collaborated with industry, academia, and Custoria to advance next-generation semiconductor ecosystems, and is a recognized speaker and contributor to IEEE and technical program committees. So now let's welcome our speaker, Dr. Giri, to give us this talk.
Thank you very much for the warm welcome. Let me start sharing. So, Bo, if you can stop sharing, I can start. Okay. Okay, I hope you all can see my screen. Very good morning to all of you. Thank you for joining this IEEE CASS webinar. My name is Janvi. I work at NetApp. And today I'm here to talk about AI-driven semiconductor systems. I'm really excited to be here and it's coming from the industry where I've spent more than 14 years now. I'm really excited to have the opportunity to share with you how this industry has innovated over the years. And myself, being in the industry, have witnessed some of the major technological developments that have contributed to the level of innovation and automation that you can currently see. I'm particularly excited to share how AI is driving transformation in the semiconductor industry and what role data has to play in design and autonomous manufacturing. With that, let's look at the agenda for my talk today. So my talk is basically going to focus on the 4 components of the semiconductor ecosystem. And in the end, as I cover all the 4 components, I would also like to share what does the path looks to the forward development of this industry, and what is the call to action from the community that we are participating in. So we'll start with what the AI and silicon imperative is. What does it mean actually, and how semiconductor industry is contributed to the AI revolution? Then second comes the data part of it. Without data, basically, whatever innovation that we're seeing is practically impossible. And what does it mean for the semiconductor industry landscape itself? How is data as a foundation enabling the autonomy and the autonomous manufacturing as we are seeing? What does it mean from perspective of chip design? Autonomous EDA has been the key enabler for advancing the AI revolution. What does the landscape of the industry looks like? How is AI contributing to the design productivity? And what does it mean in terms of scalability and security paradox that the industry is facing? We will then look into what does autonomous semiconductor manufacturing means. What does it actually mean? All of that, how does it tie into the factory where actually the chips are getting manufactured, and how the AI revolution is contributing to the path to the lights of fabs? What does the collaborative roadmap looks like between the technology that is enabling the industry, at the same time, how the industry is playing the role in enabling the technology itself? With that, let's look at the AI and the silicon imperative. This section essentially would cover how AI is contributing, why essentially AI is becoming the key enabler for silicon design manufacturing, and what are the forces that are driving the autonomousity that we are seeing. So let me just quickly highlight, about the semiconductor industry itself. The global semiconductor market is entering into this AI revolution, where the projected revenue for the industry itself has already exceeded the 1 trillion 1 trillion benchmark that was projected for 2030. So the industry is accelerating at a huge scale. And what actually is contributing is the revolution of AI to it. Now, what does that mean in terms of the economical impact? Whenever we talk about AI, the first thing these days comes to our mind are all the LLM models that are enabling the generative AI technology. So if you think of it from that perspective, you can think of like the Claude, the Chat GPTs, the Geminis and all. But if you, from the fundamental aspect of it, is it really the models that are enabling the AI race, or what is behind those models? So if we dive deeper into it and look at how the AI technology compares to the decade-old technology, which is the cloud technology, and see what the economical impact of it is, we can clearly see that where we are in the really early phases of realizing the potential of generative AI. So the majority of the income or the revenue that is generated currently, is it coming from the infrastructure that is enabling those AI technologies? So if we are currently in the phase where majority of the investment is going into the CapEx, that is your infrastructure. Over the decade or so, as the technology gets matured and more applications start building on it, this triangle, as you see here, is going to represent similar to the inverted triangle that we are realizing right now for the cloud technology. And the fundamental enabler for that is the silicon behind it. If we don't have the advanced chip designs, if we don't have the advanced manufacturing capabilities, we won't be able to realize the potential that the AI has to offer to us. And that is pretty much evident how the silicon has powered the 4 eras of computing, right from the early 1990s to the 2020s plus, where we have seen the evolution going from microprocessor to internet mobile to cloud, and now we are in the AI factory evolution. So silicon is a crucial enabler of how the AI potential is being realized currently in the terms of economic impact it has brought in. If we focus now on from what does it mean in terms of at the transistor level, we can clearly see that the growth of transistors, as projected from the Moore's law initially, we have kind of exceeded that in terms of the number of transistors that go on a silicon chip. If we just compare in terms of the numbers of transistors that were present on one silicon chip, we can clearly see that from millions and we have now in billions, and then eventually it is projected to 1 trillion. So the sheer scale of transistor growth has enabled the performance and the power efficiencies that we are looking at. And that is like the most vivid proof of how our semiconductor industry has innovated. Now, as you may have heard in the industry that Moore's law is essentially no longer, being applicable in the traditional context as it was devised before. And the reason is that we are essentially now hitting the limits of traditional geometrical scaling. With that, the industry, I really need to appreciate how the industry has innovated is that it has come up with different technologies that is keeping the Moore's law still alive. And those technologies, instead of focusing on the traditional geometric scaling, it is now looking into innovative architectures and innovative hybrid bonding solutions and three-dimensional integrated circuits to enable the kind of performance requirements that are needed to enable the AI revolution. So, even the industry is saying that we cannot scale down further. The industry has been able to innovate and come up with technologies through heterogeneous integration of chips and advanced packaging technologies. So what we are essentially now seeing is that the now industry is shifting from a conventional linear supply chain model to a more collaborative chiplet ecosystem. Now, in terms of how the semiconductor industry is structured, we can consider the industry to be divided into two segments. One is on the design side, and the second is on the manufacturing. They work together, and the inputs from the design to the manufacturing and back from manufacturing to design are crucial so that we have this closed feedback loop so we can accelerate and innovate at the pace that the industry is demanding. So if we focus on the design aspect of it, think about it, it is more in terms of defining the technology, designing how, what kind of specifications are needed, figuring out what kind of RTL is needed, and then based on that, how would that translate into a basic at a layout level? So then comes the physical design aspect of it, and once that is done, then it comes at the last stage, which is the sign off on tape out stage. Once the design is ready and is taped out, then comes the manufacturing. And it's pretty amazing that something as simple as silicon can translate those complex circuits into something that can, we can manufacture into a functional device. The value of these old technologies is actually realized after full integration. So from an industry perspective, considering the complexity of the design and the manufacturing, there is a lot of focus is that if we can somehow reduce and reduce the time it takes from the design to realize, to come to manufacturing. So shrink that tape out cycle. And at the same time, whatever learning that we have incurred in the initial phases of manufacturing can be translated back to the design. So instead of waiting for 2 to 4 months after the design is taped out and then we have our first manufacturing, can we somehow shift left and feed that learning at the very early stages of manufacturing to the design so that we can accelerate the learning and reduce the time it takes for an IC chip to be manufactured. So that is, so this is like a very complex ecosystem where there is a lot of dependencies between the several components. And this is a very simplistic view that I'm sharing with you today. Now, if we focus on the semiconductor design, as I highlighted, it is the industry is looking into how quickly they can tape out a design from the specification and enter into the tape out phase itself. So, what is so complex about the semiconductor design that it is so important for us to get that chip realized right from the spec to actually manufacture? What is so complex? What are the factors that are contributing to the semiconductor design phase and making it uniquely differentiated in terms of the challenges it results? As I highlighted, this is a multi-stage iterative optimization problem, and it requires a massive amount of compute data and orchestration involved. The front end part of it is where we are looking at the logical creation of the design. It involves several interdependent flows, right from RTL coding to simulation and functional validation. And the focus of the front end design is to ensure that the design that is being realized is functionally correcting and is able to capture the behavior at the gate abstraction level itself. And then comes the physical design, where whatever specs have been formulated at the front-end design level actually gets implemented. So the focus here is at the floor plan, the placement, the routing, and the timing aspect of it. The specifications being formulated into the front-end part get actually translated into manufactural geometry. So the focus here is to look at how the design is being optimized for power, performance, and area. And once that phase is complete, then comes the sign-off and the tape-out phase, where the focus is on whether the design that was realized from the front end and translated to geometrical layout at physical design is actually manufacturable or not. So there are a lot of checks that happen with respect to design rules, with respect to layout validity, with respect to timing, power integrity. And the focus here is to get a design ready that can be actually manufactured. And then once that GDS is ready, then that it goes into the manufacturing phase. So as you can see, it is not a linear pipeline. It is a highly data-intensive flow, and it's an iterative. So there is a lot of iterations that happens and a lot of learning that feeds into from one phase to another phase. So it's very, with that level of complexity, we are expecting that we don't see any sort of tape out delays, because if one tape out gets delayed even by a few weeks or months, it actually cascades into lost market windows. And you may have seen that happening in the industry itself, that the product release kind of schedules also gets pushed out just because the design was not taped out as predicted based on the schedule that was initially shared. So that leads to lost market windows. It leads to losing out in competition and also causes significant revenue loss. And then if we look into the semiconductor manufacturing, that is way, way more complex, as I was highlighting. It is a confluence of technical, operational, and multiple ecosystem coming together. So the conventional, if you look at the number of process steps that are involved for any advanced technology node manufacturing, there are 1,000+ process steps that are involved. There are multi-million-dollar tools that get deployed to realize that manufacturing about it. So there are so many process steps that are happening, and even if one of them doesn't function at the desirable level, it again cascades down to the follow downstream steps, and then that also delays the entire cycle of how quickly a wafer can be realized from a bare silicon to a fully manufactured, tested, packaged IC chip. So then at the same time, we need to understand that manufacturing is heavily CapEx oriented. As I highlighted, there are multi-million-dollar tools involved here. So a single mistake or a drop of like a few percentage drop in yield can cascade into a multi-million-dollar impact to it. So it's a very tight process window that the industry needs to operate so that they meet the desired yield. So it's a long multi-stage and multi-domain process, and the impact of the design and the manufacturing being uniquely complex and being like the separate segments of the industry, heavily dependent on each other. But if you look at what it results in data silos, because of the way the industry is currently structured, the data that is getting generated or being leveraged to make this happen is getting fragmented. With regards to the complexity that we saw in design and manufacturing, it becomes obvious that there has to be a significant automation that is needed so that we can meet the kind of timelines that are needed. If you just think about it in terms of how much time it takes for a design to actually being realized from the specification to being taped out, it's close to 18 to 24 months. Then add 3 to 4 months time of manufacturing. And if you look at how the AI models are currently being released, it's every 2 to 3 months you are getting it. So in order for those AI models to function and to deliver the value, the silicon has to progress in sync with it, or at least try. So the industry is actually trying to catch up, and so they can make the silicon ready so that these models can actually be realized in terms of the value they're supposed to bring. So there is tremendous pressure on the industry to reduce the tape-out cycle. However, there is an increasing design complexity that is coming into it. There is a lot of focus on how we can leverage AI and data so that we can accelerate the tape-out cycle. And this is what essentially the tagline you can hear in the industry is AI for design and design for AI. So not only you need AI to help you reduce this tape-out cycle, so increase automation, increase frameworks that you can quickly tape out a chip, but at the same time, this is actually the AI that is making the chip design itself. So there is this nice, kind of a dependency here that you need AI for design, but you also need design to enable AI. So automation pressure in that sense is tremendous on the industry, how effectively one can leverage AI so that we can meet the market demands and shrink the tape-out cycle as much as it can, so to match with how the AI models are themselves being developed. And if you look at for the semiconductor manufacturing, it is no different. There are so many. AI is not new to the manufacturing industry. Early 90s, we have been leveraging AI to do many of our tasks that can be automated and require minimal human intervention. But the pressure of automation is way more. Initially, there were siloed applications that would come in and build on the data, whatever it was, in that particular process step, and try to build the models for that to kind of, to automate some of the learning and the decision making that has to be done. But now we are not just thinking from those siloed AI applications. We are thinking from perspective of how we can actually go from that co-pilot mode to agentic mode. So there is a lot of emphasis on how this siloed AI or AI-assisted mode can be translated into fully autonomous agentic frameworks. And what is it is actually coming out as the industry is moving toward those automation-based frameworks is that the data is becoming essentially the real bottleneck. As I highlighted before, both on the design and the manufacturing segment of the industry, there are so many interdependent segments and workflows that working together, and there is a data that is not only leveraged but also is getting generated. But the data resides in those fragmented components of the industry. So, in order to ensure that the data flows continuously, so that the AI agents can come in and make decisions based on that and enable the autonomy that we are looking for, we really need a unified data fabric that ensures that the data layer connects the design, the fab, and the test in real time. Now, in terms of what are the key drivers that are pushing the semiconductor workflows towards autonomy, is basically evident from those numbers that I have highlighted here. The fab equipment spending is accelerated. As you can see, it has been projected to rise to $151 billion by 2027. There is a significant shortage of skilled workers that will be needed to support the scale at which the manufacturing industry and the design industry is growing. So by 2030, it is projected that we will need 1 million plus skilled workers. At the same time, the backend operations cost is also increasing. And from a sustainability aspect, it is very important that as we are building those factories to expand the scale at which we can manufacture, we make sure that we are meeting our natural resources target, so that we are conserving our environment and not creating environmental issues that will be concerning to the human race. So there has been an escalating number of investment that is going on in the industry. There is a critical talent gap, the rising cost, and the sustainability criterion mandates that we introduce automation as soon as we can. Now, how, as I highlighted, the data is a crucial enabler of any sort of automation that we are looking for. For this industry especially, there is multi-petabyte of data that is getting generated. The data essentially resides in fragmented architectures, and that is kind of becoming one of the bottlenecks to enable the autonomous design and manufacturing. So just to give you some idea of how the data, how data intensive the semiconductor design landscape looks like, we can see that there are thousands of jobs that gets launched. So there is a significant amount of parallel compute that is happening. There are iterative design optimization loops from RTL to verify to synthesis and physical. So there is a significant dependency between the different segments of the design process itself. And we are generating millions of files. So there is a huge explosion of data that is getting generated in form of files and metadata that needs to be versioned and shared. At the same time, the industry is now moving, is heavily looking into going on-prem and cloud. So because of the teams being geographically distributed and the kind of compute needs that are needed, the industry is shifting towards hybrid infrastructure, which helps solve some of the cloud bursting needs that are required. So it's a data intensive system which is characterized by massive parallel compute and millions of design files and at the continuous optimization loops, so that we can accelerate the tape out cycle. And on the same, if we compare the data landscape for the semiconductor manufacturing, it is amazing. A single minute of a gigafab generates massive data volumes across the process steps, the sensor data, the equipment systems. So if we look at per minute of a gigafab's manufacturing operation, there are 75,000 wafer move events that happen per minute. that data that gets generated and collected from an equipment is order of 95 gigabytes. And if you just think about from a UV lithography data that gets generated, just one of the tools of the multi-million-dollar tools that are out there, it generates close to 10 gigabytes of data. There are 15,000 sensor readings that are getting generated per minute as we are talking today across the fab tool fleet. And the number of events that are getting tracked per minute as the wafer is moving right from the bare silicon to fully manufactured phase, there are close to 360,000 recipe step events that are being tracked. So these numbers are huge, as we can see, and how the volume of data that we are generating is amazing, both in the chip design as well as the manufacturing. In terms of how AI is looking like in the industry, you can see, as I highlighted, AI is not new to the industry. Early 90s, we have been leveraging AI, both design and manufacturing. It comes in a different form, though. The initial focus was more on the static analytics of it, where systems as FDC, APC, scheduling kind of came into place. And then, as I was highlighting, it was more focused on the AI-assisted mode, where AI in form of machine learning algorithms, classical machine learning algorithms came in, leveraging supervised, unsupervised algorithms to make decision-making easier, which is essentially where human-in-the-loop AI or the co-pilot phase. And now where it is heading to is the agentic AI, where a lot of focus is coming into how we can build multi-agent orchestrated frameworks to accelerate those workflows. And if you look into the chip design, this is already happening. If you have seen talks from Cadence, Synopsys, Siemens EDA, all of those major three EDA vendors have leveraged agentic AI in some form or other. So we are actively working in this era right now, and where it is moving to is a fully autonomous production or a fully autonomous design, which is the AI factory phase. So, the foundation of all that lies in the analytics and the control loops that were built. And now where we are heading to is a fully automated agentic orchestrated mode. And data is something which is the foundation of enabling the intelligence and the autonomy that is needed. And if we look at how the industry has kind of, needs to overcome issues to enable the intelligence and autonomy, you can clearly see there is emphasis on the scaling crisis as, the EDA tools and the manufacturing is evolving to meet the scaling needs. The data infrastructure gap already exists. I highlighted that the data is fragmented across the data blocks, which is creating a significant bottleneck. And at the same time, in order to, as we are addressing the scaling and the data infrastructure gap, the path forward essentially looks like a scenario where we have standardized data models over those fragmented pilots, and then we can actually move from an assistive mode to a fully autonomous manufacturing. So the industry is actually requiring unified data frameworks that can enable the cross-layer insights, the predictive analytics, and the real-time decision-making across the entire value chain, which is required to meet this multi-petabyte gap that is existing in the age of 2-nanometer fabrication. And in terms of where this is basically current architecture breaks, you can see that there are several stages or several segments of both design and manufacturing workflows where the data is getting generated, but it is is not flowing smoothly as it is desired. So, the EDA tools are generating real-time data as they are bringing more and more AI into the design phase. There is a significant emphasis on inspection and metrology so that we can measure the things quickly and provide the insight back in the manufacturing process. But again, that data is being generated and being restricted into the inspection and metrology phase. there is a lot of operational silos. So the manufacturing execution system itself that that store a lot of operational and telemetry data, they are struggling with the disparate data sources and creating silos within itself. The test data requires different models to function, so their data again resides into their ecosystem itself. And then last but not least, the engineering itself. We like to maintain our own notes and logs. So there is a lot of unstructured information that is present still in hard copies, and that is basically kind of creating another bottleneck and how to bring that knowledge into the automation itself. So this is because of this kind of patchwork of partially standardized systems, our data is getting fragmented. So what does it mean as understanding those challenges and the complexity? What does autonomous EDA means for chip design? So if you just look at how the EDA market has grown over the years, we can clearly see that the market is expanding at a 9.4% of compound annual growth rate. And that is amazing, amazing development. And that the contributors to that are, as I highlighted, are the technologies that are going beyond the traditional geometric scaling. It involves multi-die, 3D integrated circuit kind of configurations that are contributing to the significant growth in the EDA industry. North America maintains majority of the market share with the fabless and the IDM leadership that we have. And the global market itself for EDA is projected to nearly double by 2032. And essentially, it is coming because of the need for the advanced node designs and the kind of AI workloads that we're seeing. The three big emerging players of the EDA industry, as I highlighted before, are Synopsys, Cadence, Siemens EDA. The rest, so if you look at Synopsys itself, recently they acquired Ansys, so that has to expand their simulation and analysis capabilities. Cadence is heavily invested into bringing multi-agentic frameworks, so their recent acquisition highlights that. Siemens EDA is also bringing a lot of innovation with respect to all the agentic framework for their broader manufacturing industrial software ecosystem. And then the rest is included by specialized tool vendors, as I've highlighted here. All these three vendors actively partner with foundries, example TSMC, for getting the advanced node certification. And at the same time, what the industry is seeing right now is a lot of emerging startups that are leveraging machine learning for verification, debug automation, LLM-based code generation. Some of them I've listed here, like Chip Agents, Bronco AI, to name few of them. But there is a lot of new startups that are coming into the industry and kind of reinventing the industry just because of the generative AI revolution that as I highlighted before. And how, I touched upon how AI is crucial for design and design for AI, but how is that transforming the design productivity? So Synopsys' AI solutions are leveraging technologies like reinforcement learning to explore trillions of design parameters. So there is a lot of focus on that. Cadence has Cerebrus AI Studio, where they are enabling engineers to manage multi-box SoC implementation in parallel workflows. As I highlighted, Chip Agents, Bronco AI, efforts from Cadence, etc. A lot of emphasis on how we can automate the verification process itself, as it consumes 60 to 70% of design effort. So there is a lot of machine learning coming in, agentic frameworks being leveraged there. And as I highlighted, Siemens EDA is also investing different technologies so that they can automate some of the aspects of the EDA design flows themselves. So if we look in terms of the maturity or where the gains are realized across EDA applications, we can clearly see that the verification debug process and the synthesis optimization are the ones, and design productivity and implementation speed are the key ones that have been benefited. There is still work needs to be done on the power performance area improvement aspect of it, but the rest of the in terms of how you can leverage AI to increase the productivity as well as improve the speed, there is a lot of automation benefits already being realized across various EDA applications. And the next aspect I wanted to touch about, besides automation, is the scalability and security paradox. As I highlighted that, the industry, the chip design industry and the EDA tools are leveraging AI to accelerate the learning and the design process itself. But at the same time, it is required, the compute needs that are resulting are also growing significantly. And at the same, often, it's very difficult for your on-prem architecture to meet the kind of compute needs that are required. So the industry is now looking, is moving towards getting more scalable cloud-based solutions, so that as they need the compute, they can quickly move the data to the cloud, leverage the compute flexibility that they're getting, and then bring back the data on-prem. But this, this crucial scalability security paradox is always there, because even though the cloud is offering unparalleled, scalability, IP sovereignty is what is very crucial for many of the foundries and the design warehouses, which is creating a fundamental conflict as we are advancing in the 2-nanometer technology nodes. Now, from the semiconductor manufacturing perspective, how AI and autonomous manufacturing is currently being developed, I would like to highlight the idea of self-optimizing fab that Elon Musk shared in his recent era fab announcement, where the vision that Elon Musk has for his fab is going to be where the entire semiconductor life cycle would be present on the same floor. So he has this vision of having design, memory, logic, fabrication, testing, and packaging to be all under one roof. And the core idea behind that is so that one can create fast recursive loops that are required for improving the chip design. And essentially, that is what the whole vision of autonomous factory is what going to be based on, is that how you can create that fast recursive loop so you can get the learning at the same pace as you need to get that learning being deployed. So from the fab context, what does an AI factory architecture means? So there are 4 critical architecture pillars that are required to enable the autonomous manufacturing. First is the unified data access. In order for any sort of automation to function, the automation frameworks need to have an unparalleled and significant with significant speed access to the data that is being underlying those generators. So how we can ensure that the data is AI ready from all the sources, how we can do that at reduced latency, and how petabyte scale storage and high-speed networks can contribute to that accessibility. Then that once we have the unified data access established, then comes across the metadata of the files or the data that is getting generated. How do we ensure that metadata is standardized so that we can leverage the benefits of generative AI to do intelligent search and embed that knowledge itself into our AI ML pipelines? So a full traceability for all manufactured data or design data is ensured. How do we ensure that the compute data locality is maintained? As I highlighted, the computing needs are growing significantly. So how do we ensure that the compute data locality is ensured so that as the data or, as hybrid architectures are being leveraged, there is, the data movement and the latency are meeting the requirements. And then last but not the least, and the most important, is that how do we ensure the governance and security? The data is being, is scattered, is being leveraged by multiple segments of the design and manufacturing flow. How do we ensure that the right security parameters are implemented so only the flows or only the agents that are required to access the data are accessing it? So this is going to be one of the critical aspects that one cannot ignore as they are designing their automation frameworks. And in terms of what does that entails into the factory scenario, it allows you to implement advanced methodologies for process control. It helps you to reduce your equipment downtime. So predictive maintenance is one of the major benefit of implementing that automation. Virtual metrology is another area where a significant impact is being realized as it minimizes the physical measurements. So you're optimizing your tool time. So it's enhancing the throughput as well as helping the industry to take data-driven quality checks. Significant utility realized from yield and root cause analysis perspective. This is really important so that we can quickly identify the defects, and then the information can be fed back so that those defects don't occur again, and yield can be improved over the time. And then all that kind of ties down into how do we ensure that the scheduling and the dispatch are optimized to meet the workflow and the cycle times that are needed real time. And backend optimization is significant area where all the automation needs are realized when it helps you to leverage AI to improve the overall equipment efficiency, so it can reduce the operational costs. So that that again translates down to the financial impact of how AI is contributing to optimize those crucial back-end areas, which are like assembly, packaging, and test. So that all kind of ties down. These are like few of the crucial enablers or areas of where AI is significantly helping in the semiconductor manufacturing functions. And in order for the whole thing to tie back to the stage autonomy, it will be only realized as once we move from this bounded autonomy phase, which are where we are currently operating, to a full autonomy. And what does that essentially it means? Well, in the full autonomous for autonomous factories, we'll have systems which will operate independently for most of the tasks. Human involvement will still be there because they need to be there to ensure that the key strategic goals are met and the complex problem solving is being realized. So human focus will still be there. But what the automation will do is to enable this cross-domain decision making, which is required at the scale that we have just looked at. And in order for all that to come in realization, there is a significant collaboration is needed from the industry, which includes your equipment, inspection test vendors, the fabs and IDMs, EDA vendors, the IT and the data infrastructure providers, and the standard bodies and consortia. So without a collaboration between all those different entities that are out there, the realization of automation is not going to be possible. So what does the path forward looks like? As I highlighted, automation is becoming important. AI is significantly changing how semiconductor industry is being structured. So what does the path forward looks like for the industry? So with respect to that, as I highlighted, there is a significant need for a collaboration across different segments of the industry, which not only just the tools and the factories which are manufacturing, but also the EDA tools, the IT, the infrastructure aspect of it. And the various consortia that are working to make this AI innovation possible. But core is what is going to, behind everything is going to be the data. So until we figure out how do we standardize the metadata, how do we reduce the data compute distance, how do we build this cross ecosystem trust, this will be a task that will be difficult to realize until that collaboration is built into it. So the future of AI factory or AI automation in the semiconductor essentially will belong to this ecosystem that shares the operational details among each other. With that, I would like to thank you all and we'll be happy to take questions.
Thank you, Jerry. Thank you very much for a wonderful talk. And we have some questions in the Q&A, so you can check that.
Oh, okay. Let me open that. 1 second. Oh, it's in the Q&A. Let me quickly stop sharing. Okay. Let's see. All right. Here I am. Okay, so okay, so I see one question that is being posted in the chat from Don Harris. So it's more like seems to me more like a comment that virtual metrology sounds like a contradiction of terms. Metrology tells the difference between design and reality. So Don, do you want to come, if Don can come off mute and he can maybe share a little bit context to the comment before I give my insight to it? Is that something we can do? Okay. Okay, Don, do you want to come off mute and share your context?
Hi.
Hi.
Can you hear me? Yeah.
Yes. Yes.
Yeah, when metrology, you're measuring what the actual output of a process is. Virtual tells me you're using something like a digital twin, which projects what the outcome should be. Metrology is what the outcome was.
Right. Okay, so I think what you were highlighting essentially is kind of the discrepancy in what metrology essentially means and the virtual aspect to it itself, because metrology essentially entails physical measurements, and now we're seeing that virtual metrology is going to replace that. So how do they how does the two aspects tie together? So let me share my perspective from coming from the industry itself. So why even virtual metrology? Why even we are talking about virtual metrology? And it's not new to the industry. I mean, the literature goes, early 90s or 80s around about virtual metrologies. But the whole concept is that can we leverage algorithms and models to mimic what actually how the tool functions and how the tool will yield the measurement. So if we can build mathematical models to simulate that, then maybe we can optimize the usage of the equipments itself. Because most of the time what happens that these physical measurements are destructive in nature. So for example, when those silicon wafers are going through SEM, you're essentially destroying those pattern structures on it. You cannot do anything further with that. But if you can model how, if you can take those measurements virtually, and this is not a new concept. I mean, we can see that in different domains. But if we can mathematically model that functioning, then first of all, we are able to reduce the number of wafers that need to physically go through that destructive kind of metrology phase. So that impacts your cost. Secondly, the wafer cost. Secondly, it comes in the equipment usage itself. If we have all the, if we can eliminate some of that physical measurement, the time that the equipment needs to conduct those measurements through those virtual metrology, then we are able to optimize the equipment usage itself. And then the third aspect that comes to my mind as well is that you can actually efficiently, you can develop your workflow around virtual metrology so that learning that those models are generating, that can be fed back right away without going through the entire manufacturing cycle itself. So that is my thoughts on how virtual metrology is relevant and being utilized in the industry. Okay. Next question I see is from Shivanand Kulkarni about who are the major fabs and their market share. So currently, if you look at from the manufacturing factory perspective, we have TSMC, we have Intel, we have like if I just focus on the logic side of it, the logic chips manufacturing is from TSMC, Intel, Samsung. And if you look at the memory, then it is SK Hynix, you have Samsung as well, you have Micron, and that is something that, these are like the major fabs that come to my mind. Market share for TSMC is definitely leading in that aspect. And then, the rest are following. But yeah, I don't have the exact numbers to quote here. Any more questions?
Hi, Jeremy. Actually, I also have some questions.
Yes, please.
Oh, I think there's some additional questions in the Q&A.
Yeah, that is what is the fab for RFIC chips? Sorry, it's not on top of my mind. I'll have to look up and get back. If anyone have from the audience, if they can chime in, that would be great too.
Yeah. So actually, I have some questions from the perspective of the AI. In your opinion, we know that to fully leverage the data that to produce in the manufacturing process, that we can either use the kind of the frontier closed source model, or the fab or the like the EDA companies, they can build their own models. So from perspective of the data, so do you think that which is kind of the better choice, or is there any kind of strategy for some kind of hybrid use, or maybe different type of models, maybe they have kind of different applications? Yeah, and another question is about the data curation. So do you think that is there any kind of trend or the kind of the emerging concepts that they need some kind of the community level kind of the standard for those the data curation policy or the
Right.
product, yeah, across the community? Yeah.
Yeah. No, that's a great question. And I will answer the second question and then come back to the first one. So with respect to the data curation, there is significant effort going on in, various consortiums that are industry, like SEMI, for example, I mentioned. There is a lot of effort going on from SEMI in terms of coming up with those standards. So they partner with various, industries in the ecosystem, which is your equipment vendors or your, IDMs or fabs, to basically come up with standardized ways to build those data sets so that entire ecosystem can benefit out of it. So that is one of the major focus of SEMI itself. Then going back to your first question, I believe that was more around the model building and the data kind of, aspect to it. And how currently models are being with the industry, right? So as so semiconductor industry is unique compared to software industry. So, in software industry, there is a lot of, open source frameworks are there, right? Like there are open source data set, open source libraries, open source tool that the industry people can leverage it and then build and contribute to those and keep. So the software industry grows at a different scale compared to what our semiconductor industry is, because it's just because the nature of the industry itself. So semiconductor industry is very IP kind of concerns. There are a lot of IP issues there. So nevertheless, the industry has contributed in terms of some, we can see more open source data sets and open source models coming into it. But still, in the industry, every factory or every design company, they would build their own AI models because they want to have control over how their data is being leveraged. But that is how the nature of the industry, and that's what I highlighted, that like the data is fragmented. It is existing in different silos. But in order to realize the vision that Elon Musk has painted, we need to ensure that all of them operate together in a cohesive manner, and we need to have everything under one floor, which is a very ambitious vision to have. So unless that kind of, I'm really hoping that with that kind of vision, we will start seeing more sort of data sharing between different ecosystem collaborators, and maybe that will result into some unified frameworks which will connect those separate segments, and then maybe we may have answer for some of the question that you were highlighting in terms of how data kind of being leveraged from both the segments. So
so in that case, maybe like some technique like those that privacy preserving, those that federal legal stuff, yeah, maybe can be useful that in practice.
So let's see how Elon Musk builds his Terafab, because that's the vision he has painted as well.
Okay. Thank you so much. I think there's another questions. Yeah.
One more question, yes. So this is comment coming from Yonis. Can you comment on the lack of incentives to share data across EDA, fabrication, tests, supplies, etc.? In fact, with the increase in the semiconductor market to over 1 trillion a year, there is even less incentive to share data following your current comment. Good one. I know. I hear you. That is true. As you were just discussing, right? I mean, there is this whole, maintaining their own sovereignty and control over the data that gets generated. But it is, it will, as I highlighted, so much you can do it when you work in silos. There is a big, in order to implement the vision of autonomous AI factories, you need to have a way that the data gets, flows smoothly right from the design to the manufacturing phase and back to the design. So, yeah, understood, realized that yes, there is less incentive, but at the same time, if you want to realize that vision of having autonomous factories, those data silos need to be broken. And let's see what Elon Musk comes with, and maybe Terafab will show exactly what does that mean, and I'm eagerly waiting to see, and maybe that will promote more data sharing. So.
Okay, so I think thank you our speaker again. So this is a very wonderful talk, and also thank everyone to attend our this month's actually CASS webinar talk. See you next month. Thank you, Javi. Thank you very much.
Yes. Bye-bye. Bye.
Thank you, everyone. Bye.